Okay, this is worksheet 11. We went over this yesterday, but due to my lapse, we did not record this, so I'm re-recording this for you. Um, this is not going to be showing you the solutions to all 9 of these problems. 3 for the goodness of fit test, 3 problems for the test of independence, and 3 problems for the test of homogeneity. What I'm going to do instead is take one of each of these types of tests. Of course, they all use the chi-square distribution. And hopefully by looking at those 3 problems, numbers 3, 5, and 10, and you already have the solutions. I've published those in the announcements yesterday. So hopefully with this video going over these 3 problems, one from each of the 3 types of tests using chi-square, you'll be able to do your StatCrunch calculations for all of the problems. Now remember, we do have office time tomorrow. I'll be online from 11:30 to noon. It's a short window. We can extend that if need be. So if you have any questions before you hand this in, it'll be due tomorrow by midnight. And if you have any questions, you can email me, or you can get into our Zoom session tomorrow starting at 11:30, and I can answer your questions. All right. So we'll skip 2 and go right into 3 here. All right. And so let me read the problem again. And I believe that there was some confusion on which set of data represented the observed, which set of data represented the expected frequencies. And so let's go over that again now. I think I straightened it out yesterday, but just to be sure, let's go over it one more time. This is an example of a goodness of fit test. Okay, so it says here the city of South Lake Tahoe, California, has an Asian population of 1,419 people out of a total population of 23,609. Now, here it says, suppose that a survey of 1,419 self-reported Asians in the Manhattan, New York area yielded the data in the table. Okay, so we see 2 columns of data versus the first column of the ethnicity subgroups of Asians. Okay, so in this problem, we'll conduct a goodness of fit test to determine if the self-reported subgroups of Asians in the Manhattan area fit that of the Lake Tahoe area. So the survey represents the Manhattan sample, so we'll consider that to be the observed data. Okay, so now after having identified the O's and the E's, we'll be ready to go and perform our test using our chi-square goodness of fit test statistic. Okay, so the null hypothesis is that the distributions are a good fit. That is, the self-reported subgroups of Asians in the Manhattan area fit that of the Lake Tahoe area. So again, the Manhattan area will be considered the observed data, And the Lake Tahoe area is what we're comparing ourselves to, so that represents the expected frequencies. So the null hypothesis is that there is a good fit with Manhattan and Lake Tahoe for these different subgroups, and the alternative is that there's not a good fit, okay? Alpha is 0.05 in this problem. Remember, it can be 0.1, it can be 0.04. We know that the significance level is at the discretion of the researcher doing the test. So in these examples, we've chosen 0.05 as our reference significance level. Okay. And now when we go into StatCrunch, we can populate our spreadsheet with two columns, the expected and the observed. And then we'll go into the action window using the stat super function, the chi-square test statistic, the goodness of fit test function, and the chi-square test statistic, okay? So let me go ahead and demonstrate that. All right. Okay, so here we have the Lake Tahoe data. Remember, there are 7 subgroups, and here are the Manhattan observed values, okay? And now we can choose the stat super function, come down to the goodness of fit test here, and use the chi-square test statistic, okay? And now in this action window, we're asked for the column with the observed, and that's going to be the Manhattan column, right? Okay, and then the observed column, the expected column is the Lake Tahoe frequency. Okay. So again, the survey is based on the Manhattan feedback, and we're comparing that against the known Lake Tahoe frequencies. Those will be the expected, okay? And now we hit compute, and here we get our results, okay? It's not a good fit because the chi-square statistics is way out in the right tail. And furthermore, that's emphasized by the fact that the p-value is very small, okay? It's very likely to be very close to 0, okay? And so now the other thing that we can do is compare this huge value to a critical value using the chi-square distribution with 6 degrees of freedom. Remember that in a goodness of fit test, if k is the number of subgroups, then k minus 1 is the correct degrees of freedom. So now we can go to the chi-square calculator. So let's go there and choose chi-square, and then do the following. Let's give it the correct degrees of freedom, which we know in this example is 7 minus 1, or 6. And then select a tail probability of 0.05, reverse this so that we get the tail probability. And when we compute, we get a critical value of about 12.6, okay? And notice that the chi-square statistic, the chi-square test statistic is over 2,000, way much larger, or much farther to the right. So it clearly falls in the rejection region there. and we'll reject the null hypothesis that there's a good fit. Okay, so let's go back to the document now. Okay. Oops, sorry. Okay. So here we see the critical value for this test at the 5% level with 6 degrees of freedom. And now we can base our decision on these statistics that we've just calculated. And so our test statistic is much larger than the critical value, okay? Or we reject H naught since the p-value is so small, okay? And let's see, let me zoom in on this a little bit. Okay, so here's our conclusion based on what we've done in StatCrunch. We've calculated the test statistic. It's much bigger than our critical value for 5%, or wow, I keep running into this this Zoom. All right. So let me go back to all right. Okay, so let me go back up to 200 again. Okay, and hopefully I can avoid this this ghost zooming that's going on. Okay, so we reject the null. P-value is very low for the test statistic. Another way to say that is the test statistic is very large in comparison to the critical value. And we've used that two-sided approach in all of our testing problems, calculating the p-value or calculating a critical value for the specified significance level. All right. Okay, so that's number 3. Let's go down into the set of problems using the test of independence based on the chi-square statistic. Okay, so I want to do number 5. Here it is. Okay, and number 5 says, let's see, let me get this picture out of the way. Car manufacturers are interested in whether there is a relationship between the size of car an individual drives and the number of people in the driver's family. Okay, so the relationship that we want to study, we can reword it in terms of is the characteristic of family size, which you see here, there are 4 categories of family size and 4 categories of car size. And are these two related or are they not related? Are they independent? Okay, if they're independent, they're not related. Okay, we know that from probability. Okay, and so our test of independence is again a test comparing observed and expected. Okay, it's a little bit of a different format here than our other test, our test for goodness of fit. Okay, all right. So let's go back to the slide that outlines our procedure, and you'll see it's quite similar. All right. Okay. So we can rephrase the null hypothesis simply to say the two variables are not associated, there's no relationship, they're independent, okay? Versus the alternative that they are associated. There's some correlation between the two variables, all right? And remember when we were talking about linear regression, we were trying to understand if there was a linear relationship between two variables, okay? Certainly they weren't independent. We saw that there was a correlation coefficient that sometimes was very close to 1 in absolute value, which gave us a good indication of not only an association, but a linear association there in that problem, okay? Now, the other thing that we want to be aware of here is that the degrees of freedom changes for this type of contingency table. So what we're going to do is simply, we'll simply count the number of rows and the number of columns. And the degrees of freedom is the product, the number of rows minus 1 times the number of columns minus 1. So in our data set up here, notice that we have 4 rows and 4 columns. So the degrees of freedom will be 4 minus 1 times 4 minus 1, or 9, okay? So we've calculated now the correct degrees of freedom, and then we can go into our chi-square calculator, figure out what the correct critical value is at the 5% level, just as we did in problem 3. Okay, and we'll go to StatCrunch and do that. And then in StatCrunch, the procedure that we'll use is given to us in the applets superfunction. We'll choose contingency table, fill in our data in the action window, and then perform the test in StatCrunch, okay? So let's go ahead and do that. So there are 2 twists in this scenario. First twist is we've got a contingency table with R column, with R rows and C columns, and we have a special function in StatCrunch that will do the calculation of our test statistic here, which is the sum again of the observed minus the expected squared divided by expected, okay? So what we need to do in StatCrunch is fill in the contingency table, and that'll give us a way to compute our test statistic and its companion p-value, okay? So let's go ahead, let's go back into StatCrunch and do that, okay? All right, and let's see, here's the data over here where we've got our data reproduced in the spreadsheet, okay? And remember, you can take your document that I posted for you, and you can simply copy and paste right from the Word document, okay? If you want to just highlight and then do a Command C and then paste that right into your StatCrunch spreadsheet. Okay, that's how I did this. Okay, just copy and paste from the Word document right into StatCrunch. Okay, so we get our contingency table here reproduced in the spreadsheet. Okay, so let's now choose applets. And you see under the applets super function, there's a choice here. Let's choose this function, contingency table. All right, and we can go ahead and type in here are row labels, and our row labels are basically family size 1, 2, 3, 4, and 5 plus. Okay, so again, let me just abbreviate those to save time. So we'll call family size 1, F1, comma, no spaces, F2, and F3-4, and then F5 plus. Okay. Okay, sorry. All right, and then our column labels are the types of cars. So we have a sub and compact car, just abbreviate that as sub, midsize, full size, and then van and truck. We'll just abbreviate that as van. Okay. Now, when we hit compute here, we'll come up with another dialog where we'll go ahead and type in our data. Okay. So here are the family size subgroups listed down the rows. And then across the columns, we see the car size. All right. So let's go ahead and fill in the frequencies as given to us in the data. So we type in this first column here, 2020, 2020. Similarly for mid, 35, 50, 50, 30. Next column would be full size, 40, 70, 100, 70, 40, 70, 100. Oh, no, darn, okay. 100. Let's see. Okay. Okay. 40, 70, 170. And then the last column, the van and truck data, 35, 80, 90, and 70. Okay, so there we've reproduced our contingency table given to us in the problem. We've reproduced this in StatCrunch. If we compute, we get our test statistic of about 15.8, and that has a p-value of about 0.07, which is big enough to exceed 0.05. That's our significance level. So remember, when the p-value is high, H0 will fly. So we'll accept the null hypothesis, right? And let's go back now into our Word document, okay? And follow through with our steps again, listing in the first step, the claim, there is a relationship, okay? And let's just read the whole thing. The claim is that there is a relationship between the size of the car and individual drives and the number of people in the driver's family. Okay. So we're trying to test whether these two variables are independent or not. And then in terms of H0 and H1, we can simply say that they're not independent. That would be H0. Sorry, that they are independent, okay? And versus the versus the alternative that they're not independent, okay? So there's the proper way to set up your test. Again, alpha is our usual significance level of 0.05. Again, there's nothing sacred about 0.05. It's just an arbitrary number that we can use for a significance level. It can be 0.01, 0.10, anything we want, but for illustration, let's use 0.05. That seems to be a commonly acceptable significance level. And then you saw from our calculation we just did in StatCrunch that the test statistic was 15.828, okay? Okay, there's our chi-square test statistic that we've calculated based on the data given in the contingency table, okay? And we can also find the critical value using our chi-square calculator. Again, we have to identify the correct degrees of freedom here. The contingency table for this problem, remember we have 4 subgroups of family size, 4 subgroups of car size. So the correct degrees of freedom would be 4 minus 1 times 4 minus 1, and that gives us the 9. Furthermore, the p-value for this problem that we just calculated in StatCrunch was about 0.07. Okay, so we've got our 2 ways of deciding whether to reject or not, comparing the test statistic and the critical value. Okay, and let's look at the other approach here, which is our p-value. Our p-value is high, so we don't reject the null hypothesis, okay? Or another way to say that is our test statistic here is larger than the critical value. Sorry, it falls to the left, it's smaller. It doesn't fall in the rejection region, which would be to the right of this. And here is our graph, again, showing the contingency table and the statistics for this particular data set. I did not reproduce the graph showing the critical value. Let's do that. So we'll go back to StatCrunch. All right. Okay. And remember, we're going to use our calculator for chi-square. That's listed under the stat superfunction. So we'll choose calculators under stat, choose chi-square in that sublist, and now we can go ahead and give it the correct number of degrees of freedom, which is 9. We'll put 0.05 in the right tail. So we need to change that, and we get our critical value of about 16.9. Okay. So anything that would fall to the left of this critical value would indicate that we do not reject. Otherwise, we would reject if it was bigger. But in this example here, you see our 15.8 is smaller than 16.9, and therefore we do not reject. And furthermore, our p-value is bigger than 0.05. And that's another criterion that we've used for the decision, okay? So that's all given here in the Word document, okay? So that's the test of independence, okay? Now, finally, let me do problem 10 here. And, do we need the graph showing the critical value here? I don't have it in here, do I? I could easily copy and paste it. Okay, we can always copy and paste these graphs right into our document, our Word document. Okay, so just for fun, let's go ahead and control click. So I'll copy this graph and paste it right into our document. Okay, and let's see, let me see if we can shrink that up. No, that doesn't work, does it? Okay, so let me try and insert it down here. So I'll just paste it right here. There it is. Okay, let me see if I can. Let's not fool with that. Okay, so there's our critical value chart there. Okay, and so that identifies the critical value as 16.9. Okay, so let's go down to the last problem and work out that problem here. That would be a homogeneity test. Okay, and the procedure to decide whether two distributions are basically from two random variables are from the same distribution. Okay, are they homogeneous? They may not be from the same distribution. So this test tries to reveal if we get a good fit. For example, in many of our two sample or one sample tests for the mean, we had to assume, especially in the t test, that the samples came from a normal distribution. Okay, so we could use this test to compare our data set with the normal distribution, and if it turns out that the test is positive in the sense that they are homogeneous, the sample is basically a normal distribution, we compare it to a normal distribution, then in fact, we can proceed with the t-test when the sample sizes are small, okay? So the alternative, the null here is that they are homogeneous against the alternative that they're not, okay? So again, in the t-test case, if we compare the data with the normal distribution, we would like to accept the null hypothesis, or we would like not to reject, okay, and assume now that the sample does come from a normal distribution. So that's one application of how this would be used. So let's go to number 10 now, all right, and we'll use it there. Here's number 10, okay. All right, so number 10 says, the fisherman is interested in whether the distribution of fish caught in Green Valley Lake is the same as the distribution of fish caught in Echo Lake. Of the 191 randomly selected fish caught in Green Valley Lake, 105 were rainbow trout, 27 were other trout, 35 were bass, and 24 were catfish. Of the 293 randomly selected fish caught in Echo Lake, 115, 58, 67, and 53. Okay, so let's perform a test to see whether the distribution in Green Valley Lake is the same as Echo Lake. That's what we're doing here. We're comparing these two distributions. Okay. All right, so our null hypothesis is that, yes, the two are basically coming from the same population, so that there is a homogeneity in the distribution versus they're non-homogeneous. Okay. All right. Okay. So again, our data here from the problem, sorry. Okay. Okay. So here we have again two variables. We can table this data in the distribution of Green Valley Lake for the fish versus Echo Lake. Okay, so we would have, let's say, 4 columns and 2 rows, the rows representing the location, Green Valley Lake versus Echo Lake, against the columns, which would be the distribution of the subgroups. Okay, we've got 4 subgroups here: rainbow trout, other trout, bass, and catfish. Okay, so here's our contingency table here, all right, where we've listed Echo Valley and Green Valley down the rows, and then the subgroups of fish across the columns, all right? And let's go into StatCrunch now. Let's see, let's, okay. All right, I'm not going to be able to, I'm not going to be able to copy and paste the table. All right. Let's see. Okay. And I don't think I have it in StatCrunch yet. We'll go ahead and reproduce it in StatCrunch. Okay. So I think the quickest way to do this is I'll copy the data and then type it into StatCrunch there. Okay. So this is Echo Valley, Green Valley. Okay. All right. Okay, so I've copied the data down. Let's go into StatCrunch now. Okay, and type in our data, and then perform the test of homogeneity, again, using applets and contingency table. Okay, oops. Okay, so I'm going to type in here. Let's see. Let's go right into the contingency table. I don't need to reproduce the data here. Okay, that's kind of nice. All right, so let's go to the contingency table, and our row labels are going to be Echo Valley, let's go ahead and just type it out. It's not like we have lots of categories here. Okay, and Green Valley. And then the subgroups of fish, there we have, let's see, we have rainbow trout, other trout, bass, and catfish. Okay, so I'm going to abbreviate those as rainbow trout, other trout, bass, and catfish. Okay. Okay, and all right. And now we can enter our data here. All right, so Echo Valley, the values were for rainbow trout 115, other trout 58, bass 67, and catfish 53. Okay. For Green Valley, the numbers are 105, 27, 35, and 24. Okay. Now, if we compute, we get two values here, our chi-square test statistic and its p-value. Notice the p-value is small. It's less than 1%. So right away we see that we're going to reject. All right. Okay. We can also calculate the critical value. Let's go ahead and do that as well. So we'll use our calculator for chi-square. All right. And again, the correct calculation for the number of degrees of freedom for the homogeneity test is like the test for independence. R minus 1 times C minus 1. Okay, so here our value here, okay, our value here, we have two rows, so 2 minus 1 is 1. We have 4 columns, 4 minus 1 is 3. So the correct degrees of freedom is 1 times 3, or 3. So let's go ahead and put that here. And here's our specified significance level, 0.05. And we want the probability in the tail. So we'll reverse that. And we get our critical value of about 7.8. Okay. All right. All right, so let's return to our document. Okay. And all right. And these are the statistics that we saw in StatCrunch. Okay. Okay, and so let's go ahead and summarize what we've done here. All right, so here is the summary of the results that we calculated in StatCrunch. Okay, so again, our null is that the two distributions are basically the same. They're homogeneous. Okay, and here is our contingency table, copied and pasted into our document there. Notice the labels are different because I did abbreviate the labels in our StatCrunch just now. Okay, and it's a small p-value, right? At least it's smaller than 0.05. Okay, so when the probability value is low, H naught is a no-go. Okay. Boy, this is really bedeviling me today. Okay. Okay, so let's recap here. We have, oh boy, this thing is really annoying. Okay, I think maybe we can get away with this size. All right, so specify alpha, right? And we've used alpha equal to 0.05 throughout these problems. Okay, all right. And we saw that the test statistic up, I'll show you the test statistic again. Here it is. Okay, this is what we just did. And so here we have a test statistic and we have its p-value of about 0.008, certainly less than 0.05. So when the p-value is low, H naught is a no-go, and therefore we reject H naught. And then we can also compare the test statistic with the critical value here. It's bigger than the critical value, right? 11.7 is bigger than 9.5. So that leads us, we fall in the rejection region, and therefore we reject H naught. So why do we do these two approaches each time? Well, simply because it's better to have two approaches rather than just one, okay? And it teaches you a little bit about how statistical inference is done using either the p-value and or the critical value, all right? So now our conclusion is to state that we reject, therefore the populations are non-homogeneous. Okay, remember our alternative is that they're not homogeneous. So the data provide evidence to allow us to conclude that the populations are non-homogeneous with respect, let's see, we got too many words in here. Okay, with respect to the distribution of fish, and period, okay? Or the evidence is sufficient to conclude that there is a difference in the distribution, okay? Okay, and again, sorry about this. All right, so there we have basically concluding that they're really different distributions, and the statistical biologist will want to know, well, why are they different? Is it due to some sort of environmental characteristics of the two lakes and so on and so forth? Okay, but at least his original, his preliminary analysis shows that there may be some differences in the two populations between the two lakes, all right? Okay, I'll end it there, and now I'll post this to you in your announcements. Okay.